So nuclear is really one of the surprisingly very controversial energy sources.
Is this our last lecture before our exam?
No, we have a lecture next week.
I thought it was just a revision.
No, I don't do revision. I do lecture till the last minute. We do lectures.
Okay, thank you.
So nuclear energy is controversial because people who like it really like it, and people who hate it really hated it. And so one nice thing about nuclear energy is it's really doesn't have any greenhouse. So any scenario where you want to cap the CO2 in the air will have to involve nuclear energy. Okay. So and those are the nuclear reactor in the USA. We have so many. We are the largest country in the world with nuclear reactor. Second to us is France, and third it used to be Japan. And when nuclear energy was envisioned, people were super excited about it. They thought that energy will be for free. The electricity will be so cheap, we will not know what to do with all this electricity. But it turned out that it's not really that cheap. I mean, it's cheaper, but not really that cheap because you have to worry about the cost of the nuclear fuel and storage of the nuclear fuel, the spent fuel rod after you finish it, and so all other problems related to after you finish using the fuel, what do you do with it? Because that waste fuel rod, or they call it spent fuel rod, no one would like to keep it in their backyard. And when they saw that, well, let's build a national storage area in Nevada, Nevada didn't like it either. They said, no, you cannot bring your nuclear waste to us. So there is problem associated with storage. But now let's understand where does it come from and why it has all this potential to really make electricity affordable and safe. And actually, that is the third issue. One time I did here on the NPR a few years ago, actually. I guess it was very close to Fukushima disaster in Japan. And one guy on the radio, one expert was saying, why don't engineers admit that there is no such thing as safe nuclear reactor? He said that. And no, there is. And if we just have a spoiler alert, here is, the USA just started a new nuclear reactor that is supposed to be inherently safe. So we need to understand what is the problem with safety, and is it really unsolved problem, or people can solve it, and you can have safe nuclear reactor. Okay, so first of all, how does the atom look like? So the atom look like this. There is a nucleus and there are electrons running around it. Okay, inside this nucleus you could have either neutron or protons. Neutron are neutral, no electricity charge associated with it. Protons have a plus charge. And so in an atom, the number of electrons and protons are equal. This way, the atom becomes basically balanced from electricity point of view, right? And the number of protons or the number of plus charges inside is really a big deal. The number of plus charges inside the nucleus, that's what make you hydrogen, or make you helium. The number of plus charges is what make you what you are. That's basically kind of your DNA. But the number of neutrons doesn't really matter. That's basically the fat in your body. I mean, a thin Denver or a really fat Denver is still Denver. But you change Denver height or you change the position of Denver eyes, and he's not Denver anymore. He's someone else, right? So the number of neutrons does not change who you are. You are still helium. But with 2 or 4 or 6, those are called isotope of helium. As long as you have the same number of plus, the same number of protons, you are this guy. Huh? So when you look at the mass, and they measure the mass in the atomic mass unit, okay, and you can see how small it is, 1.66 10 to minus 27 kilogram. Okay, So the mass of neutron is almost 1, the mass of the proton is almost 1, and the mass of electron is almost nothing. And so when it comes to those calculations, we will calculate the mass. It's a big deal to calculate the mass, and it's a big deal to calculate the mass really accurately, because the whole nuclear energy is based on mass. Okay, the difference in mass between the start of the reaction and the end of the reaction. So again, spoiler alert, we will start with this much mass and we will finish with a little bit less mass. That little bit less mass will release a lot of energy. And so for the first time in your career as mechanical engineer, you will hear your professor telling you the mass is not conserved. The mass will disappear on us. How does it disappear in nuclear reactor? I don't really know. I will leave that to nuclear engineers. But it's amazing. And if I have a second life, I'm gonna be a nuclear engineering professor, and I'm gonna study the mechanism for how does the mass disappear during nuclear reactor. But it's really related to what is a mass. You think you know what is a mass, but you don't really know what is a mass. What does it mean that something is 4 kilograms? What is that exactly? Because the nucleus is, and the atom is almost empty. There's like huge empty space here. All right, so what is the point of this? That we need to calculate the mass of neutron and proton inside the nucleus, and for most practical application, we forget totally about the mass of the electrons. So nuclear reaction happen at the nucleus. The electrons around, we don't care about them. We don't even think about them when we do the calculation. Okay. So as I said before, the number down there is the number of proton, and that's what make you who you are. The number of the top is the atomic, is the mass number, and the mass number is adding all the neutron and the proton, and that can change. So 1H2, that is kind of a helium. 1H1, that is a helium. 1H3, that's, sorry, hydrogen, what I'm saying. 1H1 is hydrogen, 1H2 is hydrogen, 1H3 is hydrogen. Any one something is a hydrogen, right? So those are called heavy hydrogen, okay? And what is water, by the way? Water is H2O, right? And so this guy, if we make water out of this, sometimes they shouldn't really change the symbol for the elements. As long as hydrogen, as long as it's one proton, they just call it hydrogen, right? But this particular hydrogen isotope, they call it deuterium. And so the water made out of that hydrogen is called heavy water. And it's important for some nuclear reactor. So their water is not the regular water from our hydrogen. It's made from that specific heavy water. So where the hydrogen is that heavy isotope. Okay. And so the periodic table will have, all those elements. And as the element get heavier and heavier, he stack more and more neutron and proton, and you can open the periodic table and you can see the symbol of the element neon, and 10, that's the total number of proton. That's what make him neon, because he got 10 positive charge, he got 10 protons. Now this is the total mass inside, 20.1797. Why? Because he had a bunch of neutrons and a bunch of protons, probably 10 and 10. Can we mute ourselves? Thank you. So atomic number on the top, atomic mass at the bottom, right? So 131.2, how many neutrons do you think they have in xenon? Probably 131 minus 54. That's how many neutrons. Because you got 54 protons, and each one of those proton and neutron is 1.00 whatever. So it's 131 minus 54. Okay. And those, it's not important for us in this course, huh? But those are the number of electrons in the different shells. So the electrons are sitting in different shells, and it's basically like 2 and 8 and 18, 18 and 8. And of course, those need to be equal to this guy. If you add them, the number of electrons will be equal to the number of protons, so that the guy remain balanced. So that is the periodic table. Okay, and we are specifically interested in those guys over here. So when you open them over here, you'll find out those ones. Thorium and plutonium and uranium. Here's the plutonium. Why? Those are, so 90, 91, 92, 93, 94. Specifically this guy, uranium, 92. And 238. So I said there's isotope. Not all uranium are created with the same number of neutrons. But they all have 92. All have the same number of protons. So some of them have 238, some of them have 235, some of them have 233. So this is the majority of the uranium have 238. So when I dig and get some uranium from the ground, chances are it's going to be 238. Okay. So you are looking at those numbers here will basically be weighted by the most famous or the most common neutrons, isotope. So now some of those isotopes exist in real life, like exist in nature, and some of those isotopes, we just create them ourselves in the lab. And they live for a very short time. How do they die after a very short time? For example, they will, so first of all, how do you create an isotope? Add neutron. You just need to add more neutron. If you give him one more neutron, that is a new isotope, right? So they are, why do they create them? Some of them have medical application. You will see how. But some of them are stable. So stable means that once you create that isotope or once you find this isotope, he will stay like this forever. That's a stable isotope. And some of them are not stable. How they are not stable? They, after a while, they will lose a neutron. They will eject a neutron or eject some stuff out, and suddenly he changed to something else. I mean, imagine if he lose a hydrogen nucleus out, or basically he lose a proton just get kicked out of the nucleus. He completely changed his nature. He dropped from, say, carbon to nitrogen or something. So this is called radioactivity, when he sends stuff out and he could change his identity. Okay. And while he's doing this, when he sends those things, they actually can be treating a cancer. That radiation that come out from them when they decay, they could actually kill a bunch of cells around him, hopefully a bunch of bad cells around him. And so you can treat cancer by this. Or you can actually, you digest this isotope and he's radiating like crazy, but then you put him in an X-ray picture and you can actually see where he is. And maybe he only bind himself to a special bad tumor or something. So then when you put him, you inject him in your blood, he go and he gets stuck to the bad place. And then when you put him in the X-ray, you see where he is. See, he's sitting here. That's the place where the bad tumor is. So they use them as a tracer. They use them as a radiation source, right? And for this particular chapter, we actually interested in using them for energy. So how does energy get generated? Uranium, the 92 uranium. And that uranium is so heavy that he is not really stable. He will, if you just hit him with a neutron, he will take that neutron and he will break. And when he break or a fission happen, he will break into two parts, not equal to the original parts. Amazingly, the mass disappear in you. So you start with like 235 atomic mass, and you end up with 234.993. What happened to that small part? Become energy, right? And so that is the basis of the fission energy, is that we shoot him with neutron go in, and then he break that atom because that atom is just become too heavy to stay alive, and it gets broken. You had a question?
There's the actual protons or neutrons like lose mass, like within themselves, or
So the nature of the fission engineering is a little bit more complicated because the neutron has to, first of all, it's very easy to shoot a neutron through an atom. Why? Because the neutron is not charged. So it's very easy to send. That is completely the opposite when you are shooting protons. When you're trying to shoot protons into an atom, and we'll do this, I guess, in the next few pages. We'll try to do this in the next few slides. It's very hard to shoot a protons because you will be repelled by all the other plus sitting inside. But the neutron, when he come in, he need to come at the right speed. If he's too fast, he will go through it. A neutron will go through an atom if he's too fast. So they need, and we will see how the reactor is designed, but they need to slow him down or basically thermalize so that, and send him back, then he can get captured. So there's a capturing cross-section area, which is basically tell you at that speed level, will this atom be able to capture this guy or he will go through? And again, that's beyond our focus over here. So we are a mechanical engineer. All we need to calculate or we care about is how much mass do I need to store in my nuclear reactor? How much energy is going to be released? But we will study the nuclear reaction from the point of view of basically the user point of view, not the scientist point of view. So, but I share your enthusiasm basically. I think it's very fascinating. And another story is that I really, when I finished my high school, I wanted to go to nuclear engineering. And there was only one university in my country that has nuclear engineering, and it was in another city. And my uncle lived there, but my dad and my mom refused for me to travel to that city and stay with my uncle. They said, no, you stay here, you study what we have in our city. I'm not gonna go to the, and I had to listen. So, but I really wanted to study nuclear engineering because I think it's really, really fascinating. All those things about, actually everything about nuclear engineering is actually very fascinating. But still, we are in good career as mechanical engineer because they work in one place, we work everywhere. Mechanical engineer work in everything. So, I mean, who built the nuclear reactors? Probably mechanical engineer. Maybe the mechanical engineer designed the reactor, but we are the one who's building the pumps for them. We're the one that's running the cooling tower for them. You will see that mechanical engineer actually do a lot of things. All right. So here I'm just saying that in chemical reaction, the atoms are conserved. So when C burn with 2H2, you make CH4. If you start with C, you have to finish with C. If you start with 4 hydrogen atom, you have to, they need to show up on the other side. There is no question, atoms are conserved in chemical reaction. But in nuclear, they are not conserved, okay? So you can have K and L and you end up with M and N, completely two different species. The only thing that's conserved, however, is the number of protons and the number of neutrons, or the total number. So the guys at the bottom should be the same, and the number on the top should be the same. I know that I said the mass disappear, but the number of neutrons and protons are exactly the same. Okay, there is other mass that will disappear on us. not the neutrons and protons involved. All right. So a typical problem in the final is that I'll give you those three and ask you for the fourth one. And you do like a sixth grade level math. You basically just add how many total protons? Okay, how many did, so 17 minus 4, then I need 13. And you go to the periodic table. Who got 13 guy? What is this guy? You for it's carbon. Here it is. Or nitrogen or something. Nitrogen. All right. So like this. This is the typical problem in the final. You should expect something like this. You say aluminum and helium make silicon and so 13 plus 2, that's 15. 14, this has to be 1.
Hydrogen.
20 hydrogen immediately, right? Why hydrogen immediately? Because you saw the 1 at the bottom. And 27 plus 4, that's 31. Here's 30, that's 1. So it's 1, 1. That is the first isotope of hydrogen. Right? 1H1. And you would say this guy is 1H1 hydrogen. Okay? So pretty nice. It's really easy. So and he's doing it over here. But he's also telling us now, if you calculate the mass of aluminum and helium and the silicon, you will find there's a difference in the mass. Mass disappeared on you. If the mass disappeared on you, and it's very tiny, it's 0.002 atomic mass unit. But this will release a lot of energy. How much energy is we'll see, it's gonna be E equal mc squared. The simplest and the most famous equation ever. So during my PhD, whenever I come up with a new formula for my professor, he will tell me it's too complicated. Look at he always remind me, look at the most important equation in physics, E equal mc squared. See how short it is? I want your formula to be that short. So try to reduce the number of parameters involved. So so what happened? This guy just basically sent a hydrogen. He eject a hydrogen atom or hydrogen nucleus basically out. But other stuff that can come out of the reactant, he can actually eject a electron. Can come out. How do you eject an electron out? When you switch a proton to a neutron. No, when you switch a neutron to a proton, that eject an electron out. When a neutron become a proton, that means that an electron came out. -1 went out. He get changed out by ejecting a negative charge. And if you actually switch a proton to a neutron, then you need to send a plus charge out. And so that plus charge out, we will say +1, 0. So what is a 0? Because the electron doesn't have a mass when it comes to neutrons and protons. So +1 and 0, that's called a positron. Okay? And -1 and 0, that is electron, is being ejected out. So in those kind of problem, you could end up with having -1 and 0. You would say an electron. Or you will have +1 and 0, and that is a positron. Okay? Does this make sense? So I mean, it does not always have to eject like helium or like hydrogen. You can just eject an electron in those nuclear reactors. And the neutrino is, we give it the symbol, and it's basically 0 and 0. It's very small, carry 55% of the energy. And so usually when you have electron ejected or positron ejected, they also come with a neutrino associated with them. So this process of sending stuff and changing your status is called radioactivity. So an element is radioactive is if he keeps sending stuff out. Okay? And so in this reaction, for example, radium becoming rhodon, 88, 226, switch to 86 and 222 plus what? It will be 2 and 4. That is a helium nucleus. That kind of radiation is called alpha decay. Okay, and so that alpha decay is actually not that dangerous, and a sheet of paper can block it. So a sheet of paper between you and that reaction can keep you safe from it. So years ago, Dr. Raman Singh over here, he actually had a funding from the Department of Energy, and it involves some kind of alpha decay in the experiment. But I mean, you still have to do a lot of safety inspection and stuff because of just anything related to radiation. All right. The beta decay that is dangerous, and it's when you eject an electron. So see, -1 and 0, and the electron come with a neutrino next to it. So beta decay, ejecting electron, and positron decay is when you send a positron, which is kind of the evil twin of the electron. Actually, I think it's the good twin because it's +1. Maybe the electron is the evil twin. But the point in those kind of reaction will be in the final when I block this guy, for example. I can block this one, right? And then you have to figure out, well, what is missing here? So that sodium turning into neon. So you will calculate the number. You'd say 11 and 1. I bet this is 10, and 0 and 22. This must be 22. So you go to the periodic table and say, who got 10 and 22? And that would be the neon. And so you write the set. Okay, pretty cool. So, and gamma decay, that is, you don't lose particles, but you basically lose energy, radiation. And so that gamma decay is dangerous, but we actually use it in industry. For oil and gas, they have the pipeline coming from the rig in the Gulf, and that pipeline has sand, has oil, has water, has gas, all in the same pipe. And they need to know how much is how much. So by putting a gamma ray source in this side and putting a receiver on the other side and sending that radiation through the pipe, and they can vary the level of the gamma ray depending on the absorption of the radiation between the source and the receiver. You can basically tell, I think there is like 50% liquid in this thing and 50% gas. And you vary they have like a table, or not table, triangle, where they can basically say if at different level, if you can get the radiation absorption at different level, you can basically say out of that liquid, here's how much of it is water and how much is crude oil, for example. Actually, in our own lab when I was a student, but before I started my PhD, they had a gamma source because they wanted to figure out, when we study fuel injection, they wanted to know how much volume of the engine is occupied by the droplets and how much is the gas. So they do the same thing. They send gamma ray and they wait on the other side, and they can say, well, wow, this volume is like 90% air. The droplets are very little. Or the whole thing is flooded and there is water everywhere. Okay, so it's a way to figure out just like when we do with X-ray, you can send the X-rays through you, and you can see the tissue and you can see the bones, right? It's the same mechanism. So while our element is doing all those activity, whatever gamma ray or positron decay or beta decay or alpha decay, he is changing himself, right? I mean, when he sends those things out, he changes himself. So maybe you start with 1 million atom, and within few time units, we'll see how much time units, maybe 50% of them already changed their way. Rather than becoming, they were radon, now they are radium, or whether they were like sodium, now they are 50% of them become neutral. The time where this thing happened is called the half-life time. It's the time taken for half of the population to change themselves. Okay? So let's assume this half time is like 1 day. So then the next day, what will happen? They will be finished? No, they are not going to be finished. Half of what's remaining will change their way. So then you will end up basically 1/4 in 2 days. And in third day, 12.5, and so on and so forth. So when will all the atoms disappear? Theoretically speaking, in infinity. Okay? But 50% is going to change in half-life time. And within 3 half-life time, you can just basically end up with 12.5%. So this is the other kind of problem that I'm going to give you in the final. Is to basically, if I give you the time, you can figure out, I would say in 3 half-life time, how much is left. Or if I tell you, we started with 1,000 and we end up with only 200. How much time did it pass? And so that curve is this equation. That's the equation that you will use. Okay? So this equation say what? Say n over n naught, n over n initial, equal to E, this is E, to power minus 0.69 T over T half-life time. Okay? So that number is not really any magic. This number is such that when you put this 1/2, when you make this one, when you make T equal to T half-life time, whatever this half-life time is, as you can see here in the table, here is the half-life time. Okay? So some of them, krypton is 76 minutes. And so when you see this, you always say, what is the problem of Superman? You know, in 76 minutes, the problem will be over. His krypton will be done, half of it, and he can basically fight again, right? So it's not really a big deal. And also, when it comes to uranium 238, which is what is gonna be left in our spent fuel rod, what is the half-life time? Long time. And that's why Nevada does not want to keep those fuel rods in their place, because that fuel rod will remain active for how many years? Yes, it's not gonna stop radiating. Okay, because it takes 1 billion years to lose half of them. Yes, that's an excellent question. There's a whole bunch of slides which isotope we use for nuclear reaction, right? You will see it's a big deal, and that's all the issue about Iran, and we'll explain that in a minute. But you just notice that some take forever and some finish in 9 hours, 76 minutes. Okay? So carbon 14, 5,000 years. This is actually very important, this carbon 14, that it takes 5,000 years to disappear, half-life time. Why? Does anyone know why carbon is important? Dating, right. And what's dating? To find out how old is that crop is, or this animal is. So how do they figure it out? They look at the carbon and they can see how many carbon did change in his bones. And then based on that, they would say, this guy has been there for this many years. Okay. And so they are saying, I was actually listening to this on the radio. I guess, to a lot of radio. They were saying how we are approaching the limit of the carbon dating. And after, so the scientists, biology scientists, really in kind of panicking, because after a while they will lose any chance to date things, because all the carbon will be over or something. Like, there is a problem that after 10,000 years, you cannot basically tell anymore. So this equation, all we need to do is put the ratio, get the time, or get the time, find the ratio. So if I say, krypton, in how many will be left in 20 minutes? How many of the krypton 87 will be left after 80 of after say 40 minutes. You would say 40 over 76 minutes. It should have been the same unit. This is dimensionless. So 40 minutes over 76 minutes, and you will get the ratio over here. And you will tell you, well, 25%, 0.25. That's what will be left. Okay. Or I would say, how much time does it take for 90% of krypton 87 to disappear? So krypton 87, what's the half-life time? 76 minutes. I put 76 minutes over here. And you said, how much time does it take for 90% to disappear? So what's N over N naught? How many minutes does it take for 90% to disappear? What's N over N naught?
10%.
0.1. The N is what is left, and naught is the initial. So when I say how much time does it take for 90% to disappear, then what's left is the 10%. This become 0.1. That is the largest trick in this kind of problem. When you flip, the numbers. When you ask how much is left, or how much disappeared. Okay. Very good. So, and so you can see here an example, So iodine isotope 135 decay by a beta emission into xenon. Okay. So the 53 become 54. How is that possible? He's ejecting electrons. So that's why when he reject or lose electrons, the 53 become 54. And neutron become proton. He send one negative charge and he become a proton. Okay, doesn't matter. The point is there is a reaction and determine the time required to be reduced by 90%. So N over N naught is 0.1. And you go to that table and you find out what's the half-life time for that isotope, and it turned out to be 6.5 hours. You calculate the T. So that problem would be very simple in the final. If you are listening to me right now, you know the method to be a piece of cake. Okay. Now, how much energy is involved in this nuclear reactor? The equation. E is delta mc squared, the change in the mass times c squared. If mass disappear, energy is released. So I guess there is some kind of conservation in Mother Nature after all. So the mass that you lost show up as energy. Okay. So E is mc squared. Of course, C is a really big number. How much is C? 3 times 10 to the power 8 meters per second. Square that. Square that, you got 16 zero and multiplied by the M. So for a really tiny M, you still get a lot of energy released. Okay, so that city of Tulsa, it only take 1 gram to disappear to run us for the whole day. 1 gram disappearing will power a city for a whole day. Okay, you know how small a gram is, right? Very good. So we can use this equation, or he make it as to us actually in units too. Like you can use the delta E in joule and delta M in kilogram. So 9, 10 to the power 16. But most of the time, we actually going to use this one. This one is more useful because it's delta M is already in atomic mass unit. So 1.49, 10 to minus 10. And you get the energy in joule. Okay. And there is conversion over here that take you from mass to energy. Okay. So the conversion between the mass and the energy is those units. So this is joule, BTU, kilowatt hour, megawatt day. So megawatt day is like running 1 megawatt for a whole day. And this is called mega electrovolt. So mega, that's 10 to the power 6. Electrovolt, that's the energy in 1 volt, electrovolt. So the conversion, this is actually the most of the time the calculation is done in this energy and this mass. So the mass is calculated in atomic mass unit, and the energy is calculated in mega electrovolts. Okay. So typical number, stored in the fuel. Chemical reaction, when we burn coal in a coal power plant, you get 3 10 to the power 7. Okay, or if we remember what's the heating value for most fuel, you guys remember? Like gasoline and stuff, what is the heating value? 30 megajoule per kilogram, right? We said 30, 40 megajoule per kilogram. So that's what it is, 33 megajoule per kilogram. Okay. Now, when we do uranium fission, it's 10 to the power 12. Okay, so 10 to the power 5 more. And now, if we can do fusion, it's even bigger. And what is fusion? So let's see what's fusion. So the joke, first of all, is that fusion is always, like they always tell you, fusion is 10 years away. And during my career as a student, and then as a graduate student, and then as a professor, you always get, like, not always, but for often, or like from year to year, you get like a professor in really big university say, we managed to make fusion happen in our lab. And people get super excited and they go and they check the number and they, no, there was a measurements mistake. He didn't really do fusion. And you get disappointed and you always feel that it's never gonna happen. But there is a reason to be optimistic that fusion could happen, because the current Department of Energy Secretary, they actually said they're gonna put money on fusion to really accelerate the reaction, accelerate the progress. So first of all, what is fusion? How does it work? It works the opposite of fission. So rather than breaking an atom by a neutron, and we end up with 2 parts that less, in fusion, we combine atoms. And amazingly, same thing happened. When you combine them, the result, the bigger atom that you form, has less mass than the original one. And it's the same equation. E is mc squared. Okay? So now, why this is hard? Because when I combine 4 hydrogen atoms to make helium, for example, and 2 positron, it's very hard to fuse those hydrogen nucleus together because they are plus, plus, plus. I cannot even put 2 magnets together. So in my house, when I try to, like, add this magnet for my aquarium I clean it with, and when I try to push them against, like, I can't. So how can you put 2 charges against each other? Well, how does the sun do it? Yes, because the sun gravity basically push all of them together and they have nowhere but to get fused. All that mass crunch them together. And so what are we trying to do for the last, 50 years or more? Is we are trying to do this. We are trying to make big temperature field, like very, very high temperature, so that we can fuse them together. But the material, like, we need to put the best material we ever invented in this planet. Tungsten carbides and all those very high temperature alloy, and that's not enough. We even try to, using magnetic field, we used to make this gas plasma away from the wall. So you try to confine them and keep them away from the wall so that the wall wouldn't melt. Problem is, all that effort to do this take more energy than was actually we're gonna get out of it. Okay, and besides, also the temperature does not, there is problem with the temperature, and there's problem with it required this much, 200 million degrees Celsius to do this. Say that again. Once this happen, how does the energy happen? So the energy would be the cooling of the reactor. That's what happened in fission, and that's what will happen in fusion too. So when you do this, that thing become hotter because this energy is released.
It's the torus that's in France. It's not in the pool of water.
First of all, let's make it, and then let's worry about getting the energy out of it later on. So the problem is that they are not really capable of doing it continuously and get energy out of it more than what they put into it to start with. What's also amazing is that like a commercial, like something like Skunk work at Lockheed Martin, you know, those are the team that made the SR-71 and all, like a lot of legendary invention. They actually at maybe like few years ago, 5 or 10, they said they're gonna really try to make a small fusion reactor for aircraft carrier. So if you have an aircraft carrier that runs in fusion, you know, that would be really super cool. You don't have to refuel it at all. So, but I mean, it's still under development. But what's nice about this is, what do you think is really nice about this compared to breaking fusion, breaking uranium?
Worry about dumping uranium.
Yes, you don't have to worry about any radioactive spent fuel rod. There is nothing bad that will come out of this thing. Helium will come out of this thing. How cool is that? You put hydrogen, you get helium, no nuclear waste, nothing, right? And and it's happening all over the world around us, not all over the universe. That's how stars make their energy, by fusion. So if we can just figure how to do it, our problem will be over. Okay, let's take a 10 minutes break and we do vision after that. 10 minutes break.
How far along are you guys on the truck? Like done?
So I'm barely finished up.
I'm not doing that.
Uh,
I'm kind of glad we gave us that extra week.
yeah,
Oh, are you taking any other classes there?
yeah. Taking metallurgy, it's not a big deal. And this computer method. Pretty sure you're in it too.
God damn.
Dude, that takes so much time.
I have
So-
never spent so much time on the same class at this university.
Yeah.
That damn computer class.
Like, if I didn't work, I'd be all over it. You want to learn it completely, but it's not the case.
Every time I open up one of these assignments, that's just, I haven't been outside on the weekends, like doing anything fun for like 8 weeks. This is homework. I think I had 2 nights where I stayed up through Sunday, so all Sunday night, went to work 6 in the morning, and got home and tried to turn it in, tried to do these assignments.
Yeah, that's kind of what I do too.
It's,
That's one of my weaknesses.
I'd love to spend more time in this one, but damn, just the pass.
Yeah.
Just the pass.
Yeah, I like the idea of it's pretty intense.
Oh, what what we were doing, I would find it actually difficult to do it without the code. I could still probably do it in MATLAB, most of the problems. But trying to do those problems in a language I am completely unfamiliar with, that was where, holy smoke. Are you in it as well? Or?
I took it 3 semesters ago or something. Dr.
Say,
Smay,
this guy here?
Dr. Smay. I had his first semester. He said he felt horrible after that semester, which apparently he didn't really change much because it sounds like it's about the same.
Yeah. Holy crap. Okay. Well, at least. Yeah. I thought it was like a person was in debt, I guess, this particular class, but at least it's a little bit of continuity.
I don't feel like, he started going over a lot of the initial stuff, and it's just like, man, that TCC course that guy teaches over there is just a joke.
But
Get you prepared for it, yeah.
yeah, that's not
I
part
don't
of it.
even know why he brings up VBA when he starts going over object-oriented programming. As soon as he starts that chapter, the book he told us to get, absolutely useless. And then once he got into GUIs,
Oh,
I've pretty much checked out. I really want to learn it, but as far as them presenting the knowledge in a way that's dumb enough for me to understand, I'm just not there yet.
I mean, I understand, like, I guess the complexity of that course, especially getting into, so I'm just learning programming and GUI, but yeah, I don't know. I guess he just doesn't have enough time to try to dumb it down for us.
Yeah, I think you're right. 100%. I think that's 3 classes in 16 weeks. That is, I felt like all the homework. I mean, if you would have dumped it, like brought it down to like 1, I could have spent more time individually and actually made those codes work. I think out of all the homework assignments and exams, I've maybe turned in 3 or 4 functioning programs within all of the whole homework stuff.
I'm kind of looking at this.
And as soon as after homework 6, homework 6 was the first OOP.
Yeah.
And then after that, I was pretty much from the catch. Did you at least do your survey?
Yeah, I'm trying to get to 35%.
Yeah. That will help a bit.
He's not a harsh player either.
It's not. It's
Like, if you can get like something going, even if it's just like,
even if you label where you're going at, it'll give you the point.
or even if you just put another code, you're doing sometimes.
I've spent so much time in front of this computer trying to get that stuff to work. And when he gives results, to some of them, like I would have never figured.
Oh yeah, when I watch the solution,
Oh.
like, there's no way I would have thought that.
I think I wrote in my survey. He was telling us to go online and look these up to help us. And I told him, it's like there is 1,000 Hello World programs to every code that might help me out with one of your assignments. Like, I mean, there's a Hello World for every situation you can think of. And there's Lord knows how many configurations of it. I was a little sad that class. Oh, that was a pretty fun one. I saw his post this morning. Did you read that yet?
The professors?
Yeah, Rebecca Smith or
Was it like last night or something?
yeah, I guess he read the chat. Kind of hoping it's not.
Well, I actually had to log on like halfway through that class, like over the convention.
Oh, it was brutal. Yeah, I was laughing the entire time. I'm about to have my mic on. I almost spilled my drink.
Really? What were like the other students saying?
They were just essentially he was assigning homework. It's not a big deal. It's assigning a project and homework.
Yeah.
I kind of knew he was going to give us the final fuck you. He did. He stuck with it too. But he posted something this morning about he was showing like how much money programmers and stuff.
Yeah, I did read them.
And I was like, we're mechanical engineers. I don't know anybody else that's maybe a civil engineer here and there, but those are people that program.
Yeah.
That's I don't know.
Yeah, I did see this. Stating that he was
It's just weird.
and he said last semester was the one.
All right. So let's start again. So we said fusion is still kind of science fiction, but there are hope in that Department of Energy new funding will really accelerate things. And if it happens, it will be really great. Now, what has been possible since Second World War is vision. Vision is done easily now. And the first time they achieved this was in America during the Second World War. And how does it work? A particular isotope of uranium, 235. Unfortunately, it's not the most common one. So the most common one is 238. But 235, which is 0.7%. If you dig uranium, 0.7%, not 1%, 0.7%, you will find it's 235. And that 235, if you hit him with a neutron, he will break. And you can see there is xenon and strontium. But what's even important is that 2 neutrons will come out. So you send 1, you get 2. Now those 2, it's 2 point something. But if those 2 hit the next 2, you'll get 4, you get 8, you get 16, you get basically a nuclear bomb. Okay? So, but for this to be successful, every one of the neutrons need to find another 235 waiting for him. Okay? But in Mother Nature, there is not that many. So that's why when we have a piece of uranium that we dug with only 0.7 235 is not gonna have a nuclear bomb. You need to increase the level of 235. Okay, and that's called this process called enriching the uranium. What's enriching the uranium? You have more and more 235. And the level of enrichment is the difference between raw uranium that we just dig from the ground to fuel capacity, fuel basically level, fuel rod level, which has to be 3.5 and higher, to a nuclear grade uranium when the percentage of enrichment become really, really high. And that's why if you have been listening to the news recently, when Iran said that they're gonna go to enrichment level to 20%, they will be like, why? You don't have any application that require you to do 20%. A nuclear fuel rod only requires 3.5%. So why you are doing 20%? For what purpose? Okay. So when this is not the only pass, but if you, for this pass, if you calculate the mass here and the mass there as he's did in this example, and you need a good periodic table to tell you the accuracy of those guys, the mass of each one of those atoms. Huh? I have hard time remember how to pronounce strontium. That's why I'm writing it over here. So if you calculate the difference in the mass, you'll find out there is minus 0.198 atomic mass that disappear between the reactant side and the product side. Okay, and so when you say delta MC square and you use this conversion, you'll find out that it's almost 184, 185 mega electrovolt. A good number to remember, huh? Just like I would like you always to remember that the heating value of hydrocarbon is around 40 megajoule. The number to remember is like really 200. Why? Because this is the prompt reaction. This is what will come immediately after the reaction, but then there is more decay that will happen later on. So for every vision, it's 200 mega electrovolt. And why do we need to remember this? In case we want to calculate how much energy is stored in this mass, we need to know the energy from one atom, and then we calculate how many atoms in this mass. So every atom that we're going to break is going to give us 200 mega electrovolt, more or less, 200 mega electrovolt. Okay. And so, see, typical problem in the final, huh? How much 235 required to produce 1 megawatt day? Or I can make it more interesting, and I say the city of Stillwater electric consumption is this much. Huh? And it will be in kilowatt hour or megawatt day or like any kind of joule units. By the way, can I turn this into joule? How can I turn 1 megawatt day to joule? 10 to the power 6 to make it watt day, right? 10 to the power 6 to make it into watt day. And watt day, how can I turn this to watt second? 24 times 60 times 60. Turn the day into hour, turn the hour to minute, turn the minute to second. So 24 times 6 times 60, right? That time the 10 to the power 6, you turn 1 megawatt day into watt second. What is a watt second? Watt second. What is that unit?
Joule.
Joule. Watt second is joule, because watt is joule over a second. Right? So watt second is joule. So we turn it into a joule, and then we can come to that table over here and tell ourselves, if I want this many joule, how much atomic mass unit does it take? Okay. Or you can turn the joule into mega electrovolt, and then you know that one atom is 200 mega electrovolt. So basically, this kind of problem is all about the conversion. Huh? So over here, how much of this guy 235 needed to get 1 megawatt day? Okay, and so he's saying a good number is 200 mega electrovolt, and he's saying 1 megawatt is this much. Okay, and so you see he's converting the joule into mega electrovolt by doing what? By saying 1 mega electrovolt is 1.6 10 to minus 13 joules. Okay, and so this many joule per second is turning them into mega electrovolt per second, and then he's basically saying every atom take 200, so he turned this into vision per second. So vision per second, that's atom per second. This is how many atom per second you need to break. You got it? So if you need this much power, this many joule per second, you can easily calculate how much 200 mega electrovolt you need per second, and that convert to how many vision per second you need. So he needs 3 10 to the power 16 vision per second. So then the question is, well, how much mass, how much gram will have this many atom? And then he can say it's how much per second. So that is the atomic weight. What is the atomic weight? So I'm not saying the molecular weight, because 1 molecule is 1 atom, so it's the same thing. So 235 what is the molecular weight of 235? It's 235 gram. 235 235. So the 235 gram per mole, right? That's the molecular weight. 235 gram per mole. So what is the mole? The number.
Avocado number.
Yeah. So 1 mole will have 6 10 to the power 23 atoms. So he is trying to figure out how those vision, they are basically what is the mass of those number of vision. So he's figuring out what is the mass of one atom to start with. So the mass of one atom is the mass of 1 mole divided by the number of moles, number of atom per mole. The mass of one atom is the mass of 1 mole, which is the molecular weight, divided by the number of atoms per mole. Molecular weight is 230 gram per mole, and you got this Avogadro's number per mole. So this is the mass of one atom. Okay. So if you want this number, how many vision per second he wants, huh? And each vision will make 1 atom, and each atom consists of this mass. So multiplying this number of vision per second time the mass of 1 atom will tell him basically how many gram per second he needs. And this is just day to second conversion. Okay, so 1 megawatt day is 1 gram per day. Okay, so look at those numbers at home because it's important to understand this conversion, because if the problem come a little bit different, you still need to understand how to convert from mega electrovolt to gram. So again, that's what will happen in vision. 235 get broken into 2 parts, and 2 atoms, so 2 neutrons will break through. If one of them make it to the next one, then you have a basically sustained reaction. You need at least 1 atom to 1 neutron to make it to the next one and the next one, so the reaction keep going. If the 2 of them make it, that is a nuclear bomb, because it will be 2, 4, 6, 8. But if we can keep 1 to keep going, that will be a sustained reaction, huh? Huh?
It sounds really chancy to me. I don't know.
Yeah, so now what is stopping you from reaching the next 235? That the 235 need to be nearby, so that's why the enrichment need to be 3.5 or higher. And second, you need that neutron need to be at the right speed. And when he come out of this, he's actually very fast. So when he gets broken, he need to go to something that will slow him down. Huh? So the thing that will slow him down is called the moderator. Perfect name, moderator. He moderates the neutron. They are going so fast, we need to moderate them. That moderator can be the water. The water is in the reactor is not just for moderation. The water is really for cooling. It's the coolant. The water is also the coolant. It's the one that we take the energy into it to the next turbine, waiting to generate electricity. But it happened that the water is also the moderator. So those neutrons come and slow down, get thermalized, and when they slow down, they come back and hit the next. So for this process to happen, then we cannot have one big nuclear fuel rod like this, because the atom in the middle, if it get broken and neutron come, he will have to travel so far to get the water and come back. So as a result, the reactor needs to be out of thin nuclear rods surrounded by water around them, so that the neutrons can have a chance to go get the water, come back. So you don't send him to still water to get neutralized and thermalized and come back. No, he just needs to go across the hole and come back to us. It should be a short journey. Okay. Is there anything else beside water to moderate? Yes, people use graphite to moderate. So other reactor, like in England, they don't use water as coolant. they use, say, a helium. They use gas as coolant. So then you still need a moderator. You need graphite to slow down the neutron. So you need a moderator to slow down and get him ready, and you need a coolant to take the extra energy. And if you have enough, number of neutron that will make it back and hit another 235, so you need enough 235, you got yourself a chain reaction. All right? So this description that I showed you, explained that where you have like neutron, like the rods and moderator and rods and moderator, this is called heterogeneous reactor core, as compared to homogeneous, where everything is just one thing. Heterogeneous is that fuel, liquid, fuel, liquid, fuel, liquid, right? And the guys in nuclear engineering basically designed the core of the nuclear reactor. Okay, so now. Yes, go ahead.
So this uranium has different isotopes. Which one is the pure one?
Which one is the fissionable one? So the fissionable, so the majority is in nature is 238. That cannot be broken by the regular neutron that we generate. He actually 238 will see what it can be broken with. Can be broken by fast neutrons in fast reactor, and that was China and Russia has recently been building. I'll show you how they look like in a minute. But the majority, the way that we design our reactor in the USA is we have slow neutrons that fission 235. So 235 in nature is only 0.7%, not even 1%. And that's why all our fuel rod has to be enriched first before they can be used as fuel. Okay, so he's saying over here that to achieve that chain reaction, you have to have a heterogeneous reactor and you have to have enriched fuel. Heterogeneous reactor so that the neutrons can have a chance to get thermalized, come back, and you also have to have fuel rod with a lot of 235, 3.5 or higher.
So basically that means like all the isotopes are like they are impure, right?
Not impure, they cannot be used in the traditional reactor. 238 can be used in fast reactor, and I'm going to show you next. And ask me about 238 in a minute when I show it to you, because I sometimes ask about that 238 and how we can use it to vision. Also, the fact that 238 is so much, there's so much in nature, you would think we need to figure a way to actually use it, right? And I think I read one time Bill Gates had invest money in a startup company that will take uranium out of seawater. There is uranium in seawater, and they can harvest that uranium from 238 from the seawater. So just hold on a few minutes, you will see how does the fast reactor work. But that heterogeneous design, what does it mean? It means that the fuel rod has to be like sitting in a pallet like this, surrounded by water, right? Water everywhere around them to thermalize them. Okay, so you can see the water come in, get hot, and leave. Sometimes that water would boil. They will call it boiling water reactor. So it leaves as a steam. And sometimes that water come, get hot, but never boil. It also leaves as liquid. And that's called pressurized water reactor. And recently, the US Department of Energy has been investing in only pressurized water reactor. We were writing a proposal the other day, and we had one of our friends working for Department of Energy, and we had one proposal that involved improving the boiling in boiling water reactor. And he told us, don't even bother. They are not going to spend money on boiling water reactor anymore. So the emphasis is more on pressurized water reactor. And we see why when you know what happened in Japan. All right. So what if we want to slow down the reaction? You just need to kill what to slow down the reaction? Yeah, stop the neutron. So there are something called poison rod or control rod, and they are basically poison for the neutron. They absorb the neutron, huh? And they will, so like boron, cadmium, indium, those are neutron poison. So those control rod come in, and once you put them again, the reactor is like a bunch of rods and water in between them. So in between them, instead of the water, you can send the nuclear, you can send the control rod. They eat the neutrons, reaction dies, right? And so in an aircraft carrier or submarine, that's how when the captain say forward or backward, well, the guy in the nuclear reactor basically have the kind of a really lever, not really lever, but basically all he does is just send the nuclear rod, take the nuclear rod. You put the nuclear rod in, and suddenly no boiling, water does not boil anymore, and the whole thing slow down. You take them out, and zzz, the reaction happen, and you got a lot of steam, and the steam rush to the turbine, and the turbine run the propeller of the submarine. Okay, so you would think with something like this, why would we ever have an accident? Let's always just push the nuclear rod, and we will be done. Well, in case of Chernobyl, their reaction, their reactor was, so that was done or happened. There's a good show in Netflix, I think, about what happened in Chernobyl. It's a big series, and it shows you how does the culture of the Soviet Union during the Cold War was very secretive, and they wouldn't really trust anyone from outside, and they had this problem of, you know, you cannot show that you had a mistake. There is no transparency. And so their design was such that it is like, it's kind of like metastable. It's like this. The moment you push it out of stability, it will fall. So meaning that the moment the temperature increase a little bit, the reaction speed will increase, which will make the temperature higher, which will make the reaction increase, which will, huh? So during part time or like part load. So that was happening when the reactor was coming out of maintenance, and it wasn't like fully load or anything. And our book actually do a great job telling the story of what happened. But the point is, within few fraction of a second, the temperature was so hot, the thing melted. The nuclear control rod didn't have a place to get in, because the whole thing was like a mush of radiation, of like molten core, basically. So there was no place for the rod to come and slow down. All right. In case of Japan, they actually have the nuclear rods and everything, and they claim they managed to put it in. Although another investigating committee said that they think maybe the earthquake, there was an earthquake and then a tsunami, and they think that maybe the thing suffered from structural damage during the earthquake. But anyway, the point was that yes, they managed to slow down the reaction, but even with slowing down the reaction, there's still something called decaying heat. The reactor still, even with no reaction, still get hot, and you continuously need to cool it. Continuously need to cool it, and they didn't do a good job in cooling it, and we will see what will happen in a few slides. Okay, but here is how we do the enrichment. So you start with 0.7% from the ground, and you have to put it into a pellet at 3.5%. Okay, and then those guys, you put them into like a fuel rod like this with like good glading that is sustain really high temperature. And that is what you make your core out of. Okay, and so that enrichment take you say maybe to 5%, so that you can have a good fuel rod. So if you are above 20%, that's called highly enriched, and that's probably is for you are going into a military application. And if you are less than 20% enrichment level, meaning that 235 is less than 20% of the population, that's called low enrichment. Okay, so how does enrichment happen? In the old time, 1945, here's Tennessee, it takes big area, big plan to do this. How do we do this? How we can increase the number of 235? What's the difference between 235 and 238? What is the difference? And heavier, 238 molecular weight is 238 gram per Avogadro's number. The other one is 235. One of them is heavier than the other one. We separate them. So, but it's not as simple as this. You turn it into a gas first. Then it's a heavy gas, so you add fluoride to it. And so you form UF6, and then you send it into something like this, and the heavier guy will go straight, and the lighter guy can turn around. And this happened in a stage after stage after stage and after stage, and it takes really huge power to keep running something like this. That was the first generation. The second generation was centrifuge. And you can see the people, and those things rotate, and you can see rows and rows and rows. And if you have seen the one in Iran, when they were inspecting them, you would see like they were not as tall, but there are like so many of them. So they also put a limit on the number. If the Department of the United States Nuclear Agency, they also try to put a cap on how many react centrifuge you can have, because if you increase the number, that means that you can go to higher and higher and higher and higher concentration, right? But the idea is simple also, same thing. When you send the gas, the heavier one will go to the outside while the lighter one will stay in the middle. And you can pull the lighter one to go to the next stage, which gets more lighter and lighter. So you start from 0.07 to 0.08 to 0.09 to 0.0 and so on and so forth. Okay. Still, this is a big plant and it takes a lot of energy, and people can tell this is an enrichment facility. So now recently, like maybe in the last 10 years in Australia, they actually figure out, this is like the third generation, a way to do this in a lab. So they said, well, if we have that gas and we ionize it with laser, then one of them will get charged, the other one will not, and you can attract them with just simple electric field. And so when this can actually happen in really a university lab, you don't really need big facility. Okay, and so when they did this, the American Physical Society, they signed a letter. I mean, people were split whether we should, like, this is something that should be perfected and really invested in. And of course, the scientists who invented this technique were like cheering for it, because that will make enrichment super cheap, and then we can make nuclear energy very cheap. But then the other side said, and they signed an open letter to the American government saying that they should stop that technology, because then it can basically start in people enriching all over the world without any control and without any monitoring, because you cannot really tell. And so what happened is that GE actually got the patent right for something like this, and they said that you can only develop it for us. You cannot use it for anywhere else. But still, this technology is called CLX. So it's laser enrichment technology. That is kind of like third generation. At the end of the day, you need to increase the number of 235, because that's the one that gets visioned by slow neutrons. All right. Now, that fuel rod can be in a boiling water reactor, they call it BWR, or pressurized water reactor. Funny thing is, one time I can give you multiple choice in the final, and one time I basically showed some kind of reactor, and I said, is it a boiling water reactor or a pressurized water reactor? And the difference between the two of them is that one of them, the water boil and make vapor, and the other one, the water leave as liquid. But that student looked at that sketch and he just saw that in boiling water reactor, the control rod come from the bottom, and in the pressurized water reactor, the nuclear rod were basically scrambled from the top. And he saw that if it comes from the top, it has to be pressurized water reactor. If it comes from the bottom, it has to be boiling water. No, not really. The difference is the status of the water in the reactor, not where the control rod is coming from. So how can we tell? I mean, we will see a sketch and we will see different. But there is boiling and there is pressurized, and that's so we used to have a lot of boiling, and now I think the first nuclear reactor that we build in maybe 30 years is pressurized water reactor because it's safer. Huh? So let's ask me this question when you see what happened in Japan. We will see the accident in Japan and how did it happen. Then you will appreciate why the boiling is better. So now those are using water as the coolant and the moderator. Those are the things also that I ask about in pressurizing and boiling water reactor. What is the coolant? What's the moderator? Okay. So now Canada has a certain design there called CANDU reactor, and those CANDU reactor use for the coolant and moderator not regular water. They use heavy water. So what's heavy water? Instead of H2O, D2O. What's D2O? The 1H2, the heavy hydrogen. So you actually need to make a water plant rather than making an enrichment facility to enrich the fuel. No, you make a water plant to make that heavy water. If you make that heavy water, then your fuel doesn't have to be enriched. Okay, it doesn't make sense for the US because we need nuclear fuel or we need high enrichment for our nuclear arsenal anyway. So anyway, we have to enrich. But for Canada, I guess they are not interested in making nuclear bombs, so they can run. And for other countries that are not really planning to develop any nuclear weapons, maybe that design is actually nice because you just use natural uranium. You don't have to worry about enrichment, and you don't have to go through all the trouble of proving to the world that you are playing it safe and you don't trying to develop any weapons. Okay, gas cooled reactor like in England, the coolant is a gas, whether it's CO2 or hydrogen, sorry, CO2 or neon or helium, and you need a moderator because the gas will not work, so you need graphite. So the rod, so if you see a design where you have nuclear fuel rod and then graphite next to it, that has to be a gas cooled reactor. Okay, because why would you need graphite? You need graphite to moderate the neutrons, right? Okay, now the fast neutron reactor, those are the one that actually can use fast neutrons, and they can make fission with them, and that's why they don't need moderator. But the coolant is liquid molten salt, liquid sodium. Okay, so that molten salt go and make steam somewhere else, but the reactor itself is cooled by that molten salt. Okay, and he used plutonium and uranium-238 in those fast neutron reactors. So this would be the typical problem or like multiple choice. I will show you something like this, and you can tell what is it. So you see graphite over here. So that is a graphite moderated water reactor. That's the one that blew up in Russia. That's the Chernobyl one. If you see something like this where you have gas and you have graphite, that's gas cooled. So that gas go in and make steam over here. right? Heavy water reactor, that is the Kandu design. That's the Canadian design, where you have heavy water surrounding your nuclear rods, and the water basically makes steam for you. And that is a liquid metal fast breeder. So you can see how the liquid metal is a coolant, and you don't have a moderator for it. Neutrons, as fast as they are, they can still do the fission. Okay, so this is the boiling water reactor. This is from GE, made by GE, and that's exactly the one that had the accident in Japan. So how does it look like? So the nuclear control rod, the control rod come from the inside over here, okay? And this is the place where you have your fuel rod. And on top over here, you have the steam trap, so that only the steam can go and all the oil, all the water droplets will basically get stuck. So when you see something like this with a steam trap, you know it's a boiling water reactor, because they put this steam trap, especially if you read tree, steam dryer assembly. So that steam dryer assembly basically makes sure that no droplets can go to the turbine and hit the plate and injure the turbine. Only steam can leave. So this guy is sitting in water, and the water boil on the nuclear rod. The water make bubbles, and those bubbles basically leave, and hopefully only the vapor will go through. So, and you need cooling cycle. Water basically come continuously, make vapor, go to the turbine, condense in the condenser, come back over here to boil. We are using basically the space as our boiler. And you have extra cooling cycle. Why do you have this extra cooling cycle? In case of, increased activity, or maybe the turbine doesn't need that much energy, then you would use extra cooling. So those extra cooling loop is your safety insurance policy. So accident will happen if this thing gets super hot. So our job is to keep him cool as cool as possible. So that's why you have all those redundant cooling cycle to keep him from drying out and basically melting on us, right? So the boiling water reactor. The pressurized water reactor, in a sketch like this, again, the controllers come from top. That's not really, doesn't matter. Just a cartoon. But the point is, water is continuously circulating around, and no bubble, no vapor ever come over here. This is continuously water. Now, this really hot water, why it does not boil? Because the pressure is so high. So it's very hot, but it's still liquid. Now, when it come over here in that boiler then will actually make vapor. So there are two water loops, one that goes through the turbine, condenser, pump, boiler, and one that remain here and always in the liquid state. Okay. So a sketch like this, you will see that how they are trying to say that water that goes through the nuclear reactor is always under high pressure. How? By pressurizer. What's a pressurizer? A big air tank that's basically putting the pressure on the water. So a sketch like this, you can immediately tell this is a pressurized water reactor, not a boiling water reactor, because it has a pressurizer on top. So that's your clue. Okay. So how does it look like? So the reactor is in the middle, and those are places where the hot water make steam for someone else, and then come back into the reactor. So it stay always liquid. So now the liquid coming from the condenser in the Rankine cycle come here and boil on that pipes that has the pressurized water and become vapor to go to his turbine. And each one of those guys look like a heat exchanger, a tube, a shell and tube heat exchanger. where maybe the pressurized water is in the shell side and the steam is basically going into the tube side, or the opposite. Maybe actually it's better to have the water in the pipe side, the pressurized water in the pipe side, since it's really at high pressure, and having it in the pipe side is actually more easy to happen, because you can make the wall of the pipe really thick, and you can see the steam is, the liquid is coming on the shell side, become vapor and leave. And again with a steam trap. And on the side over here, you see the pressurizer, huh? The one that maintained that the pressure here is really high enough that the water never boils. All right, so what is the difference between the boiling water reactor and the pressurized water reactor? What happened in Japan? So those are the 4 reactors that they had, and they were in the coast, and Japan has a lot of earthquake, and after the earthquake, usually there is tsunami wave, and they did expect a tsunami wave would come during the life of the reactor, so they built a tsunami wall over here. In case there is a tsunami wave, that wall will prevent the water from hitting the reactor. And they built the tsunami wall. It was like 7 meters high. How large was the tsunami wave that came, you think? Yeah, 13 meters. It came with 13 meters, and it flooded the whole thing. So they said they managed to shut down the reactor, but there's still decay heat. Okay, and that decay heat needs to be cooled, and they are fine. They actually have a diesel generator in the plant to continuously, even if the electricity was cut from them, from everywhere, the diesel will run, and the diesel basically will run the pumps, and they are next to the ocean. Water is there all the time. So I mean, what can happen bad? Well, the tsunami wave was so high, it flooded the diesel room, and the diesel didn't start, and they couldn't have the cooling that they needed. And so that decay heat. So this is the reactor that we were talking about. And look at the torus of the cooling water that they have. They have all this water with pumps that basically ready to flood this thing with water and keep cooling it all the time. But you need the pump to run the show, okay? And next to it in that room is, no, see, this is underwater. This room is flooded with water. This room is also flooded with water. What's here? Huh? No, this is actually the spent fuel rod. So the spent fuel rod, after you finish them, they still need to be cooled underwater for 2 years. You finish, there is nothing left in them, but still they are radiating, and you have to keep them underwater for 2 years to cool down. Then after that, you can let them air cool outside. So what happened was, with the diesel not running, that water get, this guy need continuous cooling, and the water level gets lower and lower because of the evaporation. And once it gets really low, the thing becomes so hot, and at that heat, the water break into hydrogen and oxygen. And you have hydrogen and oxygen, they basically ignite with an explosion, and basically the exploded and on fire. They basically, the hydrogen split and end up causing an explosion in the reactor, and the radiation basically breached the environment, and that's why, you know, people were basically evacuated. And what's said was that, so the solution is just we need to cool, and so we need to run pumps, and let's bring pumps and keep cooling. And so, but because of the radiation breach, this place was very hazardous, and so they sent only the old engineer because they don't have that many years left on them. So they kept the young engineer and they sent the old ones, and basically they just like pumped the water from the ocean and back into the ocean. And at that time, people were worried that that radiation will end up in a fish in a Walmart near your house because the fish will eat that radiation. But the problem is, what could stop this? What is bad of this design that you can solve? Why did this guy over the radio show that I was listening to one after this? He said, why don't engineer admit that there is no safe nuclear reactor? Is that guy is inherently unsafe, and is something we can do to make him safe?
You could put them underground, so where you could, if you need to, release water down in there without pumping.
So, but what is making inherently safe is this: is that he always need pump. He always need to be cool. So a safe design would be one that, so he always need you to hold him. He always need your hand to babysit him. So a safe design would be, if we die and we don't exist as human, electricity grid is destroyed, the reactor should be safe. So we need a design that is, in case of electricity shut down, he is safe, not the opposite. Right? You don't want something that always need you to hold his hand. So how can we make a nuclear reactor that doesn't need us to babysit him? Well, but still, I mean, he can explode underground, and then depending on how deep underground, it will still affect us or not. We can feed him water, so put him under the ocean or something, maybe. So a group at MIT actually, they actually came up with they made a company and they came up with a really very smart design. They basically said, all you need is like a valve that need electricity to stay closed. And in case of no electricity, in case of no like suddenly power outage, that gate will open, the fuel will spill out. And once you spill out, you get away from each other and you stop the radiation. So rather than you always have to, like he's in good, like he's always in reaction mood, need to be cooling. No, in case of no electricity out, that whole thing break down. And so they came up with that design, but also in the new, if I can just skip here over here. Right, so they tell you this is our first reactor in 30 years to build, and you say this is the reactor is evolutionary improvement over existing reactor. For example, it can shut down passively without external power or human intervention. So it's kind of like things are sitting on springs or something, and they are all need electric power to stay in. You cut the electricity, and things will basically just shut down by themselves. You need electricity to run, not electricity to shut down. Okay, so as if you make airplane that it needs fuel to land, but without fuel it will always fly. That would be inherently safe. So that's what it's needed, right? So now the problem of cooling actually is a big problem, because here is in the USA, this is our map, and in a lot of places we have a lot of fuel rod to store, and they tell you that you have to keep him in water for a few years in pool before it can move to dry gasket. This is the dry gasket. And so now all those dry gaskets, where we keep them, that's also really bad for, it's not really safe to keep nuclear rods waiting for a bomb to be thrown on them. then you'll end up with like a big mess, right? Because you cannot really clean them that easily. So one central place to secure them is one way to go, but it's very hard to find that place, right? So that's one problem. The other problem with nuclear reactor too, so safety, spend fuel rod, and the third problem is it's not renewable. I mean, we will run out. I mean, we are in the USA, we are fortunate, we have a lot of supplies. Canada also had a lot of supplies. But eventually it's not really, it's not regenerating. So that's why people thought about, well, can we use the 238? There's so much 238. And so that is happening in fast breeder reactor. So in fast breeder reactor, what happened? The 235, when you break, and it's only 0.7%, and you make neutron, that fast neutron, without thermalizing it, because you have what? Liquid metal, not water, he's not going to slow down. That fast neutron will get absorbed in 238. So 1 year, I showed them this reaction, and basically I asked them, where does this happen? And they just need to remember, that happened in fast breeder reactor. Okay, this is not the typical reaction in boiling water reactor or pressurized water reactor. So the neutron come, absorb in 238, 238 become 239, and then he lose an electron, he become 93, and then he lose another electron and he become plutonium. Now this plutonium is fissionable. Okay, and so that's the one that break plutonium, and that's why also the nuclear agency, when they go inspect other country, they take the plutonium that end up generating in their reaction, in their actual water reactor. Because that plutonium, if you accumulate that plutonium, you can make also a nuclear weapon out of the plutonium. Okay, but that is this reaction like this will allow you to burn a lot of U-238. So they call it fast breeder reactor. Why? Because a nuclear reactor working like this will actually generate his own fuel. So as he's burning 235, he's making 238 to become plutonium. And then the plutonium gets used. So he's breeding his own fuel while he's running. And so in the last few years, Russia and China actually build fast. If you just Google, you'll see how they are building fast breeder reactor, because it's a good way to generate your own fuel. So I don't know how safe it is, or what is the commercial benefit from it. So basically, does the kilowatt hour is cheaper or not? But for sure, one of the advantage that people can be interested in China and Russia is actually to have your own plutonium. I mean, that is pretty cool if you want to develop nuclear weapons. So, I mean, even if it's not, the USA has one like this, I think in Oak Ridge, but I think it's kind of research quality, not really production quality. But I'm not really sure if we have more and they don't tell us or not. But we have one in Oak Ridge, I think. I know one of my friends actually in Oak Ridge, he was working on mercury cooling. So they use, because mercury is a liquid metal, so you use mercury for cooling, and he was studying cavitation on mercury and how basically it can be used as a coolant. So that is what I have in nuclear reactors. So the homework this week may be a little bit weird, because part of the things that I'm also supposed to evaluate and report to the department is that how good you are in understanding the professional and ethical requirement of engineers. So I'm gonna send you the report that the Japanese committee. So after Fukushima, their Congress, I think they call it the Diet or something, they made a committee that basically investigate the accident to see what is, why did this happen. And by the way, when they had their accident, they lost all faith in all nuclear reactor, and they shut all of them. And when they shut all of them, they didn't have electricity because Japan does not have anything. And so when they shut down the electricity, their Honda and Toyota company didn't really produce as much. And over here in Tulsa, in the parking lots of the Honda dealer and the dealer, we didn't have a lot of cars because the supply chain. I mean, if they don't make those parts, then the factories in Tennessee or like wherever we make our Honda over here don't have, say, the engine or don't have the. So anyway, it was a really big deal, and they slowly start after. So they made this committee, and that committee made a report, which I'm gonna probably send you, maybe the introductory part or the abstract or the summary of that. And it starts by the head of the committee actually was not an engineer; he was a medical doctor, but he made the conclusion was this accident was made in Japan. So they take ownership of the accident. It's not like GE sucks and they are the one who built bad nuclear reactor. No, they said this accident made in Japan. And so they blame it on the Japanese society and the way the society is organized. So I'm gonna ask you to read that thing and basically explain in brief words what, how did this accident happen? Why do they think this accident happened? And how can we avoid something like this in your job? And so it's not really has to do with engineering. It's really has to do about what's your ethical responsibility when you see something wrong in your company or in your job. You just and so he came very heavy on the Japanese society, and he said there's inherently problem with us, and that's how we had this accident. I'm not going to tell you what, because then I'll spoil the homework. You really have to figure out what did he say. And just by answering this and understanding it right, that will give me the indication that you guys understand what is your responsibility as an engineer. Are you just doing numbers, or you are supposed to do something else too? All right. And maybe I also ask you to find out about this company at MIT and what did they do. And that also will give me an indication that you guys have. Besides, maybe just like few calculations to prepare you for the final, because the final will have few problems that include those simple problems. Huh? Conversions and the nuclear reaction. The final, that's a good question. What is in the final? So the final is comprehensive. But having said that, I am gonna probably put it heavily on the last part. Okay, because in the first part we did wind and turbo, right? In the second part we did only solar. And so since we had the solar, we had geothermal, we had ocean, we had nuclear, right? So you should expect those three guys to show up: nuclear and geothermal and ocean, right? But I can also give you two problems from the first part. And my reason for giving you two problems from the first part is not to punish you or like take points from you. It's just that my experience as an undergrad, that I get really smart in the last months. I don't know why. Every single year when I was undergrad and I'm studying for the final, I always say to myself, wow, why did I screw this up in the first midterm? This is super easy. There is something that light up at the end. I don't know, it's the hormones at the end, or just like because things accumulate and you really understand what's going on. But I see this last few weeks in the course as a chance for you to go through everything and get one big, shot and really understanding the material. And the exam is my only tool to force you to do it, because if I don't say the exam is comprehensive, you will never look at wind turbine again. You will never try to see what this efficiency equation for a Belton wheel. Okay, so it's just really my last chance to make you go through the material one more time. I'm not gonna lose this chance. Okay, thank you and have a good night.